Hi, this is part 2 of the lecture series on magnetic induction. So in part 1, we wrote down Faraday's law and we did a couple of calculations, but really we only looked at cases where the area that had been swept out by some moving conductor, where that had changed. We didn't look at changing magnetic fields or changing angles. So now I want to look at situations where the magnetic field changes. And at this point, right, you ask, well, but is that really happening? Do changing magnetic fields really cause currents to flow, right? The bars moving through a magnetic field cases we had before, they were all nice, but really we were able to explain them just in terms of forces on moving charges. There wasn't anything that was like a fundamentally new way in which nature behaved. There was no new law there. We could have done everything in essentially understanding the Lorentz force law. So do changing magnetic fields actually cause currents to flow? So let's imagine the following experiment. Let's imagine the setup like this, where I have a coil of wire, not a coil A, we could use a coil. Let's say it's like a solenoid like this, doesn't matter, some kind of spiral of wire with the windings. Then I'm going to have a magnet, just north-south, standard permanent magnet. I'm going to move it up and down. So what does that do? Magnetic field lines for one of those, right, they sort of go out like this and around, and then they go sort of further out like this. So they're strongest right next to the poles. In this, these sort of curve around back there somewhere, right? Remember this? They're strongest right here, so as I'm moving this up and down, I'm changing the magnetic field strength and where those wires are located. Now you do that, and you're going to observe, indeed, the ammeter is going to pick up a current. If the magnet is moved inside, and once it stays there, if it's not moving, you're not going to get a current. Like, there can be a magnetic field here, it's not going to create a current. Only while this magnet is moving up and down. Now, normally that's something we could easily do in the lab. We get an ammeter, we hook it up, we get a magnet, okay, done, easy stuff. If you don't have that equipment at home and you're stuck at home right now, then there's a simulation you can go to. This is one of those FET simulations that are hosted by the University of Colorado. This one's called Faraday's law. It gives you exactly the setup. It also, I think, a light bulb attached just for good measure. And you can sort of drag the magnet around and move it back and forth and watch what happens. Another thing you'll observe if you do this, or if you do this in real life, is that if you move the magnet one way, you're going to get a current going one way. If you're moving the magnet the other way, you're going to get a current the opposite direction. Right? So your ammeter might go positive, negative as you're moving the magnet. If you switch it around and you have the south pole pointing down, again it's going to reverse the direction of the current. So could we have guessed that that was a law? Or is this a random observation where somebody accidentally at one point moved the magnet close to some wires and was like, hey, what's going on here? I mean, in a sense, right, we could have guessed. So let me give you a little bit of plausibility argument. Imagine I keep the magnet right where it is. Not going to move it. And instead, I imagine I hold on to this here, this construction here, and I move it up. Right, I move all the wires together, they're solidly wound, they're not going sloppy. So I hold them up and I move them up. So in that case, I am moving wires through a magnetic field. We know that creates forces on the charged particles in the conducting wire. They're going to start moving. I'm going to get a current. Right, that is just purely understanding forces on charged particles. So moving the circuit upwards definitely gets me a current. Which direction, again, carefully think about this, but we all agree, right, that if I move this thing up as a whole, this circuit, then there'll be magnetic, it'll be currents, it'll be a conducting wire moving through a magnetic field that creates a current. But doing it the other way, I mean, isn't that the same thing? If I move the magnet, all I'm changing is how close those two are to each other. But does it really matter whether I'm moving this or whether I'm moving this? If we say no, it shouldn't matter, essentially because all motion is ultimately relative, right? Those two cases of moving this up or moving the magnet down, they're the same relative motion. Right? The situation afterwards looks exactly the same. And after all, we already kind of know that when we talk about the velocity, say, of a particle inside a magnetic field, we mean the velocity of the particle relative to the field. We always assumed so far the B fields were not moving, they were at rest, right? But if I do an experiment of Earth, the Earth is going around the Sun at 30 kilometers a second, so why did I never put V equals 30 kilometers a second in for the speeds of my electrons when I was trying to find out the magnetic force on them? Well, because the magnet was moving just with the Earth as well, there was no relative change. I sort of just assumed from the get-go that that wouldn't be an issue. So that suggests to me, okay, that relative motion is what matters. But if relative motion is what matters, meaning how is one thing moving relative to the other, moving this up is exactly the same as moving this down. Of course, it's just a plausibility argument, right? We then actually have to go out to nature and test it, and yes, it turns out that is indeed how nature works. So let's write down Faraday's law again. So Faraday's law stated, that the induced EMF, I'm going to write as a curly E, is the magnitude of the rate of change of the magnetic flux. So if you're assuming we're not moving our wire now, there are no moving parts, then what this implies is that changing magnetic fields cause potential differences. Potential differences means electric field. Changing magnetic fields, I'm going to write create electric fields. Of course, more technically correct would be contributions to the electric field. There's only one electric field in all of space. It's just zero in many places. But I think you know what I mean when I say this. Changing magnetic fields create electric fields. So now a question you might ask, wait, what about changing electric fields? Do they create magnetic fields? Like the other way around? The answer is yes, but we can come back to that later. What I want to do is some example. So let's take the following example. For example 1. Imagine I have a loop of a wire, and the wire is the loop is arranged in a square. I'm going to put a resistor here, and it's arranged in a square, side length L, and let's say there's a magnetic field that comes out straight outwards of this setup. Right, it's pointing straight upwards. The dots, magnetic field, pointing straight out of the page. And what is the magnetic field strength? So it's changing, so well, somehow I have to tell you how it's changing. Let's suppose the magnetic field strength B is given by some constant B, little b, to some value times time squared. Just because. Somebody's twiddling with the knobs on your magnetic field creating machine and moving magnets around in such a way that the magnetic field as a function of time, right, is some constant I'm going to call little b times t squared. Of course, you could check that the units of little b in this case would be Teslas per second squared. So when I multiply it by second squared, I get back Teslas. So what am I going to get for the induced EMF in this? I'm going to get d phi b dt is, so the area, the angle between the area of this and the magnetic field is 0, right? Because the area, just the flag sticks out vertically, exactly the same as the magnetic field. So I'm just going to have the area times the rate of change of the magnetic field, right? Really what I'm doing is I'm evaluating this using the product rule, A times B, but d A dt is 0, so only this part remains of the product rule. So, and what is this? The area is L squared, because it's a square. And now I just have to take the time derivative of this. It's going to be 2 times B times T. And that would be the answer for the induced EMF. If this resistor here has a certain resistance R, well, then I could find that the current is going to be the induced potential difference over R, or 2L squared BT over R. That just follows straightforwardly. Let's do another example. Let's suppose I have the following situation. Let me maybe have a light bulb this time around. So here's a little light bulb. Let's imagine somebody has this wire run really close to each other like this. And then they make a big circle here of radius r. And there's a magnetic field inside it. Let it point downwards for a change. Like this. And what are we going to make it equal to this time? B as a function of time. I should say this. Does it be, sorry, it's squished in here. B as a function of t, as a function of time, is, let me write it like this. B naught, which is some reference value of magnetic field strength, and then I'm saying 1 minus e to the minus beta t, where beta is just some constant. I'll show you what it looks like. So if you go put in t equals 0, time equals 0, right, this whole thing is just 1. E to the minus 0 is 1, so 1 minus 1 is 0. And if you wait a very long time, you put in infinity or, a million, then depending on what the value of b is, you find out eventually this whole thing goes to 0. E to the minus infinity is 0. So you end up with a final value of b naught. So it looks something like this. It's sort of the same type of thing you might remember from charging up a capacitor when you hook it up to a battery. Right, you're gonna bring it up to a potential difference. It's ultimately the battery's potential difference, but technically you never quite get there. So this is what this function looks like. The final value is going to be 0. But it's just an example here. Maybe that's a sort of realistic model for if somebody, you turn on the magnetic field, and whatever creates the magnetic field takes a little bit of time to sort of crank up. Maybe that would be a realistic shape of magnetic field strength as a function of time. but we're just going to use it as an example. So what is the induced EMF? The induced EMF is going to be the change of flux with respect to time, the rate of change of flux. Let me write it out in full, just once. d dt a b. Now the angle is again 0 because the magnetic field points straight down, and this thing is flat, so the flag sticks like straight up or straight down, because I'm only worrying about the absolute value. The cosine of the angle of 0 or 180, that is just 1. If it's cosine of 180, it goes in opposite direction. It's a -1, but it goes away when I take the absolute value. So this is this, right? This is my flux. I could write this. Let's write it in full once. dA dt times b plus a times dB dt. Right? This is when I mentioned we're using the product rule here, doing derivatives. In our case, this thing here is 0. So I'm going to have a times dB dt. The area is pi r squared. Now, what is dB dt? It's going to be b naught times, let me write it out, d dt of 1 minus d dt of e to the minus beta t. Right. So this is a bit of a practice in doing a derivative. You should all be like totally on top of that stuff, but maybe a bit rusty. So let's work this through. Pi r squared times b naught. d dt of a number is 0 because the value of the number 1 does not change with time. Math would be in big trouble if the value of 1 changed with time. So what do I get? I get minus from this minus sign here. Now, time derivative of an exponential, it means the thing in the exponent that multiplies the variable comes down. It's really a application of the chain rule, right? I'm going to imagine this here, this thing here is my function f. Then I get, sorry, that's not what I meant. I meant, I imagine that this thing in the exponent here, this is my function f. Then I'm gonna get minus signs from this. I'm gonna get df dt times d e to the f df. That's the chain rule. Make sure you understand this. Chain rule is important. So let's work this out. Pi r squared times b naught. Inside I have a minus sign. df dt is just minus beta, right? Because minus beta t, d dt of that is just minus beta. And then the ddf of e to the f is just e to the f, right? So e to the minus beta t. If I will spell it out again. So I'm going to simplify this a little bit. The minus signs cancel out. I'm going to get b naught beta, this times this, pi r squared times e to the minus beta t. So really this whole exercise is really just taking a derivative of this function up here. In a way, these cases are almost simpler. So I don't have to actually, because I'm just given a function for b, right? I mean, there's no, it's hard to come up with a problem here where you're not just given b as a function of time. Right? Whereas when something was moving or something was rotating, and there was a change in a, we had to actually figure out what the change was. Alright, so the one thing we haven't answered yet in all of this is which way is the current? So which way is the current? only worried about magnitudes, right? What's the potential difference? Who cares about direction? If I turn on a light, I don't care about direction. But sometimes you might actually want to know that. So if you want to know that, use Lenz's law. Lenz's, yeah, I think it's spelled like this. Lenz's law. So Lenz's law, it tends to confuse people. As on the minus side and the plus side, it's always just a 50-50, right? So at least you got a 50% chance to get it right, even if you don't understand the law. But we're not going to gambling on that. We're going to try to actually understand what it says. And here's what it says. And there are many ways to state it, like with many laws. I'm going to state it like this. The B field, and I say B field, I just mean magnetic field. I'm just too lazy to write out magnetic. Due to the induced current opposes the change in flux of the original B field. Now, maybe you're confused now. That's okay. We're going to make sense of it. So imagine this. Imagine I have a loop of wire, something like this. Here's my loop, and there's a magnetic field that goes through the loop. Something like this. So yes, something like this. So you can visualize what's going on. Right, there's a magnetic field straight up. This loop sort of goes around it. So the flux, right? Flux is the area of the loop. The area of this, maybe pi r squared if it's a perfect circle, doesn't matter, times b. And the flux, you can say, has a direction, namely it points up. So the notion that flux has direction we haven't really talked about, but I hope it makes sense, right? The magnetic field could be sticking out this way or that way while it points up. So, if the magnetic field just stays as it is constant, there's no current induced. Right, so it's say constant field, that implies that there is no current induced because the flux isn't changing. Flux not changing, right? And that's the thing that we need to get a current. So let's say the magnetic field is getting stronger. The flux increases. Say flux increases. Of course, it could also increase if somebody stretches the loop, right? And so there's some magnetic field lines out here that right now aren't inside the loop, but if you stretch the loop, you're going to include those, and you get more flux. So different ways of changing the flux. Say it increases. So that implies that the flux, the change in flux, is like imagine a flux like a vector that points up. It's that much and it points up. If I increase it, change in flux is also up because it's increasing. So now Lenz's law says the magnetic field I get due to the induced current is the opposite direction. So Lenz, the field, B field that is, due to induced current is opposite of up, because the change in flux is up, namely down. That's why it's a 50-50. It's up or down, right? Only two choices. Okay. So what do we mean by the B field due to the induced current? Well, so there's going to be a current. It's going to be either going this way or it's going to be going that way. But remember, if you have a current in a loop, that current creates its own magnetic field because they're moving charges. Because it's a loop, it's either going to create a field downwards or upwards. We can figure out the curly hand rule, right? If you imagine going this way around, like counterclockwise as shown, would create a magnetic field up inside it. Going clockwise would create a magnetic field down inside. We determine it with the curly hand rule. So make sure you can do that. Make sure you understand what's going on here, right? So there'll be two magnetic fields. Really two contributions to the magnetic field. One, somebody turns on this magnetic field I've shown in blue. And somebody's, turning the knob that increases the strength. But if there's a current flowing in this wire for whatever reason, that will create its own magnetic field. Lenz's law states that this magnetic field that's created due to the current that opposes not the field that's there, but the direction in which that field is changing that's there. Right? So in our case, if that is down, I'm going to continue over here. So we've got two options. Either the current's going to go this way, or the current's going to go this way. Well, just by the curly hand rule, this one, if I go around it, I can easily check, creates a magnetic field that looks like this. Whereas this one would create a magnetic field that points down. And this is just stuff you know about loops of wire creating magnetic fields. So what did we just establish? Lenz's law just told us that it has to point down. So this is our option. Oops, you can't see this one by Lenz's law. Right? So let's go through the steps again. What's the direction of the magnetic field through the loop? Okay, that tells you the flux, up or down. Easy enough. Only two ways the flux can point. Is it up or is it down? Next I ask, well, is it changing? If it's not changing, okay, we can stop worrying. No, nothing induced. If it's changing, then I can ask the direction of the change. If it's pointing up and increasing, the change is up. So the induced field, the one I drew here, is going to be down, and this is the 50-50. I can pick the right option just by trial and error. Which one of the two is it? Let's imagine the other scenario where the magnetic field points up. The magnetic field that's there already is pointing up, but it's getting weaker. Right? So let me just sort of let me modify this a little bit. Say this decreases, not increases. Then the change in flux would be down, right? Because if it's up, but it's less, that means the change was downwards. It's like when I have a velocity that points up, a little bit later the velocity is still up but less, then the acceleration is downwards. That's the idea here. So by Lenz's law, the B field due to the induced current is opposite of, well, if it's in the red case be down, then the opposite of down is up. So if it's decreasing, it would be this one. So the book actually has a really good sort of demonstration of this, and in this book here, the 4th edition of Physics for Scientists and Engineers, it's on page 846. So using Lenz's law down here, you can see the kind of all 6 possible situations. The field is up, up, up. There's no change, downwards change, upwards change. Sorry, no change, increasing, decreasing. So in the dashed arrow is the induced field. And then if the field is down, kind of gives you all possible options here, right? The only thing that's changing is the magnetic field. Of course, in different situations, you could have the area changing, and that will also affect the flux. If the area gets bigger, it's kind of the same as increasing the magnetic field strength. Getting smaller, it's kind of like decreasing the magnetic field strength because the flux changes in that way. But this little sort of, table, this little diagram is actually really useful just to get a hang of it. And it's the kind of thing, you've got to do it a couple of times, and then you can do it. The confusion that arises, the reason people mess up, is because they take Lenz's law to have the induced current create a field that opposes the existing field, not the change in the existing field. Right, this step here to go from increases, so the change in flux, this is the important part, is up. Or if it's decreased, it's down. Right, the red part is where people screw up. Because the field is up, but if it's getting weaker, the change in flux is actually a sort of downward vector. And then you have to oppose that, not the existing field. In a sense, what Lenz's law says is nature doesn't like change. Doesn't like changing magnetic fields. Okay, so practicing this is good. It's a bit of it on the homework. You just need to do a couple of examples, and then you got a hang of it. It's always just a 50-50. Right? Which way is the current in your wire? There are only 2 possible ways it can go. Okay, so that was part 2 of induction, and it really is kind of it. I mean, we haven't really talked about an example yet where the angle changes. I'm going to do that in the last video in this, I guess, 3-part series. And I'll also look at a slightly more complicated example. It's just mathematically more complicated, another application of what we're doing, where it'll involve doing an integral, but that's just more complicated mathematically, not more complicated conceptually. The one new thing we're going to do in the last video is conceptually different, is where we have something rotating. We could have a magnetic field rotating, or we could have the area, like the loop of wire rotating. We're going to look at an example like that, namely the idea of a generator, or one type of generator. Alright, I will see you in the last